Oh, so I believe last time we were here looking at this problem, and with this problem set, basically um, is just starting out, right? Exploring, basically implementing the basic result of PDF, right? Join PDF and join PMF. So nothing really special here, except that you have to kind of look at the region correctly, right, and implement the right formula. That's all there is. Beyond that, right? There's not much probabilistic concept to discuss. Right. So let's take a look at this one, right? Which is the last problem set for the last problem for this problem set. Okay. So even though it's not explicitly mentioned, right, for this problem, you need to check. But if you look at this joint density, right, that what do you notice about this density?
It's symmetric.
Well, symmetric is not good enough. For example, you could have something like this, right? And it's also symmetric. But I would say something like this is not very useful, right? So symmetric is good, but more than that. It splits, right, in terms of x and y, meaning that it's a product of something entirely in x and something entirely in y, right? Something like that won't do. And if it splits, that means they're independent. Okay. Now, that is something you can use in the problem as long as you mention it. Okay. Now, independence here is not an assumption that you make, but is something you prove, right, by observing the joint density that split, right? Notice you have to be careful about the region too, right? The region must also split, right? Whatever that means. Meaning that the region cannot have an interaction between x and y, right? The region is a rectangle, right? So most of the time, the only region that would not interfere with the interaction between x and y in rectangular coordinate is rectangular region. Okay? So they're independent, which is something you can use. Again, you may or may not use it, but it's a piece of extra information that might be helpful. And now, right, couple with a symmetry, which is valid too, right? That would make the conclusion about this as what? As one half, right? How so? Because by symmetry, px less than y is equal to py less than x. Right? And of course, the sum of these two is 1. Now, of course, right, this is something you could do, but this is like, for lack of better words, right, a dangerous method. I mean, it's not dangerous, but when you're new to this, there's a chance that you could overlook something. So the safer approach, of course, is just to do integration, right? You can do the x dy, x from 0 to y, and y from 0 to infinity. And you should get 1/2. Okay. So that's also right, available. Any question about this? Okay. So for part B, what should you do? So part B, right? You can set up as a straightforward integration. X from 0 to a and y from 0 to infinity, right? But if you notice that it splits, the eta minus y can come out here. And eta minus y, right, is the exponential, right? Is the density of exponential 1. So basically, the answer here is just really the integral from 0 to a eta minus x dx, which is the probability of an exponential 1 less than equal to a, right? It is 1 minus eta minus a. Of course, right? This is done knowing, right, all the kind of properties of the double integral and distribution and things like that. You can do it more slowly, right, and still derive the same result. That's okay. Right. Any question about this? All right. Okay, so let's take a look at this one. So the first thing, right, to notice is that, of course, it tells you that the man arrives uniformly and the woman arrives uniformly, etc., right? But taken together, because of the independence, right, this means that the man and woman together, right, would act as a independent, sorry, as a uniform, right, joint uniform on a rectangle, right? This uniform on this rectangle. And if you have a joint uniform distribution or, you know, any uniform distribution, right, at any dimension, then the probability calculation may be reduced, right, to a geometrical calculation, as long as, right, you see the region. You don't have to do complex integration because the density is constant, right? So, for example, right, question A here, right, what region are we talking about? In terms of a rectangle, what region are we talking about?
Would it be the area between y minus x equals 5 and x minus y equals 5?
Yeah, so correct, right? This translates to absolute value x minus y less than equal to 5. And so, right, it would be here and here, right? And I mean 5 and 5, right? And you kind of look at the line, right, of intersection and look at the region in between, correct? So that's where what there is. So here, right, the name of the game is really just to get this picture precisely, okay? And so notice, for one thing, right, in terms of my picture, for example, right, I got 1545 right here, right? It is 1545, and this is 0 to 60, right? So the 5 minus 5, right, you have to kind of get it down, right? So there it is, right? Actually, this is the picture, right? So whatever I drew up there, I was just some demonstration. The of course, you know, if you do double integral, you still have to get this region correctly. So, well, right. So this corner right here is what, 15 and 0, right? This is 45, 0. This is 15, 60. This is 45, 60, right? All right. So what are these two coordinates? What's the lower coordinate? I guess we already know, right? The x coordinate is 15, right? What's the y coordinate? Well, I guess what is this line? And what is this line?
The lower one is y minus x is -5. The
Oh,
higher
y
one
is x
is
minus 5. Yeah, y
yeah.
is x plus 5, correct. So this would be 15 and 10, right? This is 15 and 20, right? And well, I think actually we don't need this, but let's just plug in. This is 45 and 40, right? And this is 45 and 50, right? Okay, so now we need the area in between. What is that area? Or however you want to calculate this area, right? But what would that be?
Is it 300?
Well, so let's see, for a parallelogram, right? Which is what it is, right? Is base times height, right? That's really it. So the base is how long? 10, right? And the height is 30. So yeah, area of parallelogram is 10 times 30, right? But so what's the probability? What's the answer to A then? It would be the area of the parallelogram divided by the area of the rectangle, right? Which is 30 times 60, right? So 1/6. Who cares? All right, any question about this? All right. So what about B? What's the problem with the mineralized first? How will we figure that out in terms of the region? What would that be? So the man is the x and the y coordinate here in our picture.
The x coordinate, so it would be
So
x
man,
is larger than y.
no, right? The man is the x coordinate, is it? Is what you said?
Uh, yeah.
So it should be x less than y, right? Right first. Am I wrong?
Oh, sorry. Yeah.
Right?
Mm-hmm.
So x less than y. So we just simply have to draw the line x equals to y somewhere here. Okay, I have a spare picture here, right here, right? And so I'm not sure, right? Be careful, right? The regions don't have to be always region doesn't have to be always symmetric, right? So here, right, the line x equals to y here, right? And then I guess, of course, this is 15, 15, right? This is 45, 45. And then this is 15, 60. And this is 45, 60, right? Okay, which part do we want? The upper part or lower part? Or P of x less than y?
The upper part.
Okay, good. And what's the area of that?
Looks like 1/2.
No, right? Looks is very much deceiving. So
Uh,
do you have numbers to back it up? Is the area of the trapezoid, right? Which is what? The sum of the two bases, right? Times the height over 2.
mhm.
Is that right? So what is that?
Huh?
This base,
I think
this base.
it is 1/2. Yeah.
I mean, I'm not saying that you're wrong. I'm just saying,
Yeah.
are you sure, right? That's all I'm saying, right? I mean,
Uh-huh.
again, just because we slide a line x equals to y here, right? Over here, like I said, it could be slightly off, right? So we need numbers to back it up. That's all. So 60 minus 15 is 45, right? 45 plus 15, right? And then times this right here is 30, right? And then divided by 60 times 30, right? So yeah, 1/2. All right. Any question? So, right, these are relatively easy questions and not that hard. It's just meant to demonstrate, right, that for a uniform distribution over a region, sometimes, right, the question can be reduced to a geometrical calculation. Of course, sometimes the region can be something that even though it's geometrical, but, right, you cannot really do a picture, right? For example, if you have y equals to x squared here, okay, right, you do know the shape, but, right, there's no geometrical formula, right, simple that allows you to do that. So you still have to do integration anyway, right? But if we have the formula like parallelogram, trapezoid, that kind of thing, then we don't have to do the integration work. Right? Of course, nothing wrong with integration here, right? You can just do integration and you will get the same answer. Right. Any question? Okay. All right. So let's take a look at this. First of all, right, let's set the context for this problem. So what do we have and what do we need to find? What we have is two independent uniforms, right? One for the location of the emblems and the other one for location of the accent. What are we asked to find? The distribution of the location for the distance, right, between the emblems and the location of the accent, right, which is, let's say z, right, is x minus y, right? And by z here, I don't mean anything associated with the standard normal, right? Just x, y, and z. All right, so we need to find the distribution of z. In other words, right, what do we need to find? We need to find the density of z. Okay. So this goes back to that, basically finding the density of a continuous random variable that we talked about. Right. So what would be the first step?
Finding the support of z.
Not bad. Good, good. What is the support of z?
Uh,
What values can z take?
mm, from 0 to L.
That's correct. Right. Then what? Once we find the support, which is a very good step, that's correct. Then what do we do?
Can we draw the XY graph?
Okay. It will be a square, right? The XY graph is a square.
Yeah.
All right. I mean, that will help, but that comes later. Right? Depends. But okay, what do we do here? We draw the XY graph for what? What do we need to find the density of z? We need the CDF. Okay. With a continuous random variable, you always have to start at the CF level. You need to start with PZ less than or equal to Z. Once you find this, then you will differentiate. You understand? So this, right, is where the step of finding the probable Z less than or equal to Z is where the graph of X and Y might help, right? But so what would this be for Z between 0 and L? What would this be? Which, right, by the way, is what? Right? So what is that?
That would be the strip between two lines, like X minus Y.
Uh-huh. Good. Right.
Yeah.
So this is Z and this is Z, right? Okay. Well, we need to know these two, right? To help us decide. So what is the lower coordinate? The X is L, right? The X coordinate is L. What's the Y coordinate? Here, right? The Y coordinate is L, right? What's the X coordinate?
Uh, the the coordinates are L minus X, L minus Z.
Which one? Which one? L and L minus
But
Z for
both like the coordinates are like
really? Both are L minus Z? Are you sure?
uh
Well, no, I don't think so, right? Because L minus Z represents this part, while L minus Z represents that part. Are we sure they're the same? Let's see, right? So this line is a line y equals to x minus z, right? So that you're correct. This is L minus z, yep. And this line is y equals to x plus z, right? Well, yep, you're absolutely correct. Both of them are like that. Very good. Okay. So, okay, so how do we find this area? How do we find that area?
We can just take the complement,
Okay,
like
good.
the square minus triangle.
What would that be? What would the complement be?
Uh, would be L squared minus L minus Z squared.
Correct, because this is L minus Z, L minus Z. And then there's a half here, right, for each. So you're absolutely correct. So let's do this, right? Let's do 1 minus, right? And then L minus Z squared over 2 times 2, the whole thing divided by L squared, which is what you said, right? I mean, turn into a probability. Right, so if you simplify, it's just 1 minus L minus, the easiest way to write this is 1 minus Z over L squared, right? So that's the CDF. Then the PDF would be? I suppose. Right? I guess I missed a 2, right? Okay. Any question? All right. So as far as the technicality is concerned, right, that's what we do. But there's something that's interesting, right? Just to see that the work pays off. If this is really right what you care about for the location of the or the distance of the accent, right? Anything we can read from the density of z that would be of interest. This is beyond the problem, right? But what can we say about the distribution of the distance of the ambulance to the accent location?
It's still uniform?
Absolutely not. If you
Oh,
want to count that as a interesting thing, it's not uniform, right? Why is it not uniform? Because it changes with respect to z, right? So
oh, this is
yes,
yeah.
you said something, but exactly the opposite, right? It's interesting because it's not uniform, right? We just read wrong. But yeah, okay, good. It's not uniform, but even better, right? What can we say about it? It actually is a decreasing graph, right? For zero. Agree? What does that mean?
Hmm.
What that means is the likelihood of the density is highest close to 0 and lowest close to L. What does that mean? That means that as far as density is concerned, right, the ambulance has a high density being close to exit and lowest density being far from the exit, right? That doesn't mean it's optimal or anything like that, right? It just says that this seems good, right? As far as how we want things to go, right? Something like this probably is not good, right? In terms of distance, likelihood, right, of distance of something to right ambulance to distance of to location of the accident. Because if we want things to be right, I mean close, right? Because the blue line, the blue curve would say that it has a high likelihood to be far away from the accident, things like that, right? Again, this is beyond the problem, but yeah, is if you guys don't even realize or may not realize it's not uniform, that'll be the first thing to realize, right? And then the second thing is that, yeah, right, as far as like density is concerned, this looks pretty okay, right? Start out high, goes down low, right? Any question? Okay. So we have done part A and B here, right? Basically, we just say that if something is uniform over square, right, or rectangle, then they're uniform, right? Oh, sorry, then they're independent, right? Because you can just find the, you know, marginal and show that the marginals, right, the product of marginals are joint. And right, the circle, we also show that they're not independent, right? So the last one is also pretty trivial, right? Because right, basically it's this, right? So the probability is in this circle is pi over 4, right? The area of the circle is pi, right? So pi over 4, right? So question number 3 is pretty trivial. I mean, for these parts, right, you guys have to kind of write down the work, right, and everything, but we did it before, so I'm not gonna show it again, right? But wow, it's trivial-ish, right? But okay. Any question about this? All right. So let's just kind of do a tangential, right, on part C right here, right? Even though, of course, the answer is very easy. Part C actually is a way, right? It gives you a way to simulate pi. Okay. Or approximate pi, if you will. But when we say the word simulate, we mean randomly, right? So simulation really means that you kind of do random experiment and somehow the calculation, right, converge to the desired number via usually by large number and things like that. So what happens here, right? What happens here is basically you could do this on a computer, of course, but you could have, right, basically a, literally a dart, right, throwing target on your wall. And suppose that you have terrible aim, but it's also a good aim in the sense that your throw, right, is uniformly over the whole board, meaning that you have no preference, right, over any region. If you do that, right, and you keep throwing dots, right, onto the board, right, assuming that you can do it uniformly, which is really the hard part, which is where, right, where the computer comes in. But if you could do that, then at the end of the day, right, if you count the number of circles, dots in circle, over the total number of dots, then it will be approximately pi over 4. Or if you look at that ratio times 4, you will get an approximation of pi. All right. The question, of course, is like how many dots, right? How many darts do you have to throw in? How many trials do you need? How large should n be, right? For this to be reliable. Well, the answer is actually this is a very low convergence. It converges with rate of 1 over root n, something like that. So to make things even precise, right, for the second digit, which we already know, right, is 3.14, then you need n to be 100, right? So it's 10,000, right? So you need 10,000 numbers just to make it to the 3.14 that we know. So it's a very slow convergence, right? On the other hand, like it's kind of a no-brainer in the sense that, right, you just do uniform, and then in the end you just collect. So it's a very simple algorithm, right? From that point of view. Of course, the drawback, right, is that it is a very slow convergence. Okay. Any question? All right. All right, let's take a look at this one. This is an interesting question. It's a long one, so I'll let you guys read that for a little bit. All right. So this is a very interesting question because without the right approach, it actually is a pretty complex question to think about, right? Now, the premise of the question is pretty easy to understand, right? You throw n dots on a circle, right? And what's the probability they all lie in a half of the circle, right? A certain half of a circle. That's all there is, right? So this is a picture where that's true, and this is where it's not, right? Because it doesn't matter how you slice a circle, right? You cannot really have a half that separate them. What probability do you think that will happen? Just for fun, any guess? Not easy to guess, right? So let's see. Well, the approach here, right? I hope you appreciate that it really allows you to solve the problem. So the way you do it is actually surprisingly through the inclusion-exclusion formula. Ish, right? You let A be the event that you desire, and AI be the event that all the points lie in a so AI is this kind of a sub-event ish, right? But starting at a point I, right? Let's say here point 1, point 2, 3, 4, and 5, right? So you draw the you draw the you draw a diameter, right? Beginning at point I and going clockwise, right? So clockwise is this direction, right? So basically is this, right? This direction, okay? And so basically you see the benefit here, right, of having the clockwise direction, and this is actually a very clever move, is that it would definitively kind of like take away the symmetry, meaning that it only define a particular half of the circle, right, where the points can lie. So this is like define which half of the circle, right, we want. All right. The reason is the following, right? The problem by itself, right, doesn't really dictate, right, whatever semicircle you want, right? But that could be a source of confusion in of itself if you don't know how to control it. Because, right, like you draw a line like this, right, you would definitely look on both sides, correct? You would definitely look on both sides because either side count. But if you do that, and for all points, then actually you kind of get lost because you're like, okay, both sides, and how do I go about like, you know, looking at all of them at the same time? But when you think about it, and it'll be through the language of this event right here, that it really is enough to go through each of the point once and only look at a particular half as long as you do it consistently. That's actually the crux here, right? You can go through the points and look at the clockwise half, or you can go through the point and look at it counterclockwise half, doesn't matter, as long as you do it consistently, right? It will be equivalent to being able to draw all the points on some semicircle, to have all the points on some semicircle. Does that make sense? In particular, right? For example, this right here, right, is a P. How is A expressed in terms of the AI? A is a union of AI from 1 to n. All right. How do we know this? Well, clearly, right? If AI is successful, then that means A is successful, right? If you are able to draw, right, a line through the, right, to some point and have all the points lie in the semicircle, right, clockwise, then that means there's some, right? It's this, all the points lie in some semicircle, right? But the other direction, if A is successful, that means AI is successful for some I. Why would that be true? That means that if all the points lie in some semicircle, right, then there must be a point where you draw the line and it works. Why? So basically, right, it's really an adaptation of this picture right here, right? Where you see that here, right, you have all the points lying in some semicircle, right? That means there is a diameter, right, that contains all the points, right, within that. So what do you do in this kind of case? Well, you just have to rotate, right, the line until it touch one of the point, right, just at the edge, correct? Then if you rotate the line like that, then you will find that point, right? Notice the point doesn't have to be, right, named 1 to n in that order. It could be 0.2, whatever. But when you, if you rotate the line, right, so that the diameter touch one of the point, then, right, one of this line, right, will contain all the points in the clockwise direction. So this is also true by rotating the diameter we found in. Okay. Does that make sense? So that's why I mean when I say the AI is like a subcase of it. Any question? All right. Now part B, right, is where, right, is asked exactly because of the inclusion exclusion, right? Because obviously, if we have A as a union of the AI, then we just have to do PA as the P of union AI, right? But does the AI have any intersection? Does the AI have any intersection?
Well, they must have, like, because the semicircle is the same one, isn't it?
No. So first of all, you understand what the AI means, right? So for
Yeah.
example, A1 is this semicircle, A2 is this semicircle, A3 is this semicircle, right? A4 is this semicircle. You understand? So first of all, right, what does it mean for AI and AJ to be non-empty? What does it mean to begin with in English, in this case?
Well, there would be like a point that would be both on the the semicircle of AI and semicircle of AJ.
Yeah, okay. So first of all, right, I think I know what you mean. So first of all, right, this means, right, that you can draw a line, right, a diameter through I and J, right, and it work, right? Meaning that all the points lie in the semicircle, right, of I and J, right? But first of all, right, this cannot happen. And I think you immediately think of the case when I and J lies in the opposite pole, right? Like this. Here's I, here's J, right? And then all the other points are there, right? Something like that. I claim that this is not the right point, the right case. You see why? I claim that even if I and J are on the opposite side of the diameters, that's not right. The reason is exactly because of the direction. The direction move actually is a very important move. Otherwise, what you point out is true, right? For example, here, in this case, I draw, right? Which one works? AJ works because, but AI doesn't work. Why? Because AI actually look at this part. You understand?
Uh-huh.
So the direction exactly is what makes the AI and AJ mutually exclusive, right? Otherwise, they may have that case, this case that you're trying to draw, right? So B, AI and AJ are mutually exclusive for all IJ, right? Because well, exactly because of this picture that we draw, right? If you draw the semicircle clockwise from I and semicircle clockwise from J, right? They the semicircle, right? The two semicircles clockwise, clockwise from I and J cannot both contain all endpoints, right? Because if you have two different points and you look at the clockwise semicircle from them, right? They at the very least they don't do not contain each other, right? If you look at the semicircle from J, right, and the semicircle from I, they do not. So there must be some points that's missing. Do you understand? Any question? All right. So that's actually the clever piece. The last part will be easy, right? So what would PA be? Well, by inclusion exclusion, right? But because the AIs are mutually exclusive, it's just a sum of PAI, right? But because they will be all the same, so it's just n times PA1. Now tell me what's PA1. It will be 2 to n minus 1. 1 over 2 to n minus 1, right? Because once you have A1 fixed, then, right, all the other points must be on the same half, which is 1/2 raised to n minus 1 power, correct? Any question? So, right, this tells you that the larger n is, the less likely you have a chance, right, to be able to do this. In fact, right, the ratio quickly converges to 0. So the probability that you can find that line like that is almost 0 for n like equals to 10 or something like that, or 5, 6. All right, question. All right, if not, then let's give you a quiz, right? And we'll continue after the break. Uh, quiz. What would that be? Let me see here. All right. Let's do A. All right, for this question. All right. Any question before we take a break? All right. If not, let's continue at 7:05. Okay. Any question before we continue? All right. So, yep. So with this one, right, we're just gonna point out, I guess, right, the basic structure. We will not do the complete calculation, right? But so let's look at A, for example, right? What does it take to show that it's a joint density function? And by the way, right, are X and Y independent in this problem?
Yes, because you can separate the x times y.
I love it. No, the answer is no, absolutely not. So that's a mistake that is very easily done. You can separate the x times y, but the density, okay, the joint density doesn't just live here. And this is something you'll see also in statistics, which kind of makes a student confused. The joint density doesn't just live there, it also lives here in the support. The support for the joint density is as important as the joint density itself, which you don't see as much in the single random variable. Notice the support here says what? X plus y is
There's
less than 1. There is an interaction between x and y here.
yeah.
It is this part right here that makes it not independent. So it's very easy, okay? When you first learn joint PDF to only focus on the form of the function and ignore the support. But you will do it at your peril. So no, the answer is no, right? They're not independent. So the answer for A is pretty simple, right? You just have to state that they're non-negative, which is kind of obvious. But then, right, you have to show that the double integral, right, of what? 24xy dx dy, right? X from 0 to 1 minus y and y from 0 to 1 is equal to 1, right? To show that. Okay. And it will be to your benefit, right, to draw the region out, which is this part right here, right? Wait, x is 1 minus y, so y equals to 1 minus x, so it's not that, right? What was it? Y equals to 1 minus x, this one. Yeah, see? Right, it's this region. All right. Okay, so B and C, right? I'll just leave it for you to figure out. But notice for okay, so for let's just ask this, right? For B and C, what's the quickest way to do it? The quickest way is just to use the joint density. All right, this will be expectation of x. Right. And even though they're not independent, it is legit to say that they're symmetric, meaning that the distribution of x and distribution of y are equal. So x and y, actually here the term is called exchangeable. X and y are exchangeable. They are, yeah, exchangeable. So, or you can just say symmetry if you like here, but the answer here is also expectation of y. But that's by symmetry, right? This expression calculates expectation of x, right? Whatever that is. Any question? And this is a place where I have to mention a favorite question students always ask me for some reason. Is it okay for me to leave the question like this on the exam? What do you think the answer is? Oh, sorry. Is it okay for me to leave the answer like this on the exam? What's the answer? A big no, right? I mean, I'm writing like this because I don't need to show you how to do integration. But right, obviously writing down the integration and showing what the answer is, right, is a part of the question. Okay. Any question about this? All right. Yep. So this one, are they independent? The answer is no, right? But no here is not enough. Like saying something like, oh, they don't split, etc. That's my language to you, right? As a sort of a intuitive explanation or lazy explanation or waving hand explanation, that kind of thing, right? For a question like this, to give the rigorous answer, which is expected on the exam, you have to compute f of x, the density of x, the marginal. You have to compute the margin of y, which actually will be similar in structure with this because of symmetry again. And then have to show that somehow this is not equal to this, which is probably the easy part. That's what you need to do, okay, to show that they're not independent. Independent, actually, I think is easier because independent, if they do split, right, then you kind of see it right away. Like this, right? Again, I'm not saying that dependent, you don't see it right away. If you see this for a few times, you do. But the rigorous answer, right, is to show it through. You have to show it through the marginal PDF, right? Mm, Oops. Okay. So actually, right, part B right here asks for this. So it's kind of backward, right? It should be asked before A or whatever, right? Or assuming from part A you already found X, right? But of course, right, the marginal of X is just the integral, right, of the joint integrate out the Y part, right? But the Y here, the region is not dependent on X, so it's just that, right? And finally, for example, something like this, right, would just be the double integral over the region, right? So let's say X will go from 0 to 1 minus Y, and Y goes from 0 to 1, right? The reason is because this region, right, is nothing crazy. It interacts with this very nicely. So it's a square, right? And you just slice the rectangle, the triangle, right, over the square. Okay. Any question? Okay. Let's take a look at, I think this is the last one. So for this one, right, the main point, of course, is part B, okay? But here, right, it talks about a joint CDF, which is something I didn't mention in the lecture, right? But can we figure that out based on, let's say, what we know about joint PDF and CDF before? What would the joint PDF be in terms of what they're looking for? It'll be something like big F, A, B, C, of little a, little b, little c, right? Which is probably A less than equal to A, B less than equal to B, C less than equal to C, right? That's really it. That would be the joint CDF. And the answer here would be A, B, C, right? Because it's a uniform and independent. So nothing really crazy there, right? It just, in case you don't know what joint CDF is, it's just a natural, right, generalization of what the CDF is and the notion of joint. Okay, any question? So it's really part B, right? That is the main point. So how do we do part B?
Uh, so b squared minus 4ac would be non-negative.
Right, okay, yeah, that's a start. So it's really exactly the probability of B squared minus 4AC. It's not negative. But how do we calculate that? First of all, right, what kind of integral do we have to set up? Here, the integral we have to set up is a triple integral, right? Over the region. Right? The density is 1, so basically it's the area of the cube, right? The unit cube that is above that surface. B squared equals to 4AC. Okay. Yep. I trust that you all did excellently, right, in Calc 3. So tell me how to do this triple integral. Or, well, right. First of all, let's see if we remember Calc 3. In multiple integral, right? What is our first question when we do this integral? Drawing a picture is out, right? I don't know about you, but I'm not very good at drawing surface, especially something like new surface, right? In 3D. So drawing pictures out. What else do we have? Or what's the next question to decide? Next question to
Well,
decide is, yeah, good.
the bounds of the ABC aren't clear, I guess.
Obviously, that's the point, right? If it's
Right.
clear, then we're not going to be here sitting and talking, right?
We
But
could switch them, I guess.
yeah, so that's the question. What you're saying, right, is about deciding the order of integration. Do we do the ADBDC, CDBA? There's six possibilities. Are they all the same? Doesn't matter which one. Well, I just don't care. I just do one of them and hopefully it's right. Or is some order better than the other out of the six? Is any of them better than the other?
Well, B is has different weight than AC, I guess.
Okay, good. So what do you suppose then?
Hmm. Uh,
So what's the
not
order?
sure.
The order should be DB, right? First, and then the ADC or the CDA doesn't matter, I guess. But right, DB first, right? And then we'll decide the ADC later. Why? Because the B would go from where to where? From square root of 4AC to 1, right? So that's a little bit of B. Agree?
Well, I was thinking about what if we like we divided B squared from B squared minus 4AC is larger or equal to 0, and we just changed the variables to A over B and C over B.
I'm not so sure I understand that. What do you mean by that? You scale things
Uh,
by B, but how would that help?
so like we're essentially like um just like dividing the B from the original equation. So like the we only have two variables.
Yeah, okay, but we have a triple integral. How will your operation help with the triple integral to begin with? I understand, right? For example, that B squared minus 4AC is going to equal 0 is equivalent to saying something like 1 minus 4A over B, C over B into 0, something like that. Fine. But how would that fit into the triple integral?
Hmm.
This is not solving for equation, you know. This is about finding the
Mm,
bounds. So even though, right, that manipulation is valid, I don't think it has any place in terms of finding the boundary because this is the geometry of the region we're talking about, right?
hmm.
So no, right? I don't think this move is valuable in terms of this, right? So basically, this just tells you that B moves by itself, so you separate B out first, moving from square root 4AC to 1. Okay. Now, how do we decide the bounds on A and C? What is the bound? What are the bound on A and C? Is it 0 to 1 and 0 to 1? The answer is no, right? Why not? Even though the A and C, right, does live on a unit square, do we look at this whole square when we look at the AC part, well, when you do the integral of dB, right, from square root 4 AC to 1, what does that imply? That this must be less than or equal to 1, right? In other words, AC is less than or equal to 1 over 4. Of course, right? It's not negative, right? So there must be a curve AC equals to 1/4. And you look at the region, you only integrate this region over the region AC less than or equal to 4. Does that make sense? Which region? So, right, this is a quarter. This is a quarter, right? It's this part right here. Right? So what does that mean? What that means is this is not a single integral. But you need to do it as 3 integrals. You understand? And so something like that will be the triple integral that we're dealing with. Any question? Okay. So if not, I think that's the, oh, huh. Oh, that's not the last question. This is the last question, sorry. So one more. Okay, let's take a look at this one. All right. So let's say X, right, will represent AJ times and Y represents MJ, right? Michael Jackson, I guess. So they're both independent, right? Exponential 1, right? So in part A, what probability are we looking at? We want what? We want MJ, right, to finish before AJ. But don't forget that MJ starts at time t, right? So something like t plus y, right, is less than or equal to x. Correct? And there you have it, right? You just have to set up the double integral for this region, which is something like e to minus x plus y, right? dx dy, where x runs from t plus y to infinity and y runs from 0 to infinity. Whatever that is. Any question? Okay, what about part B? So part B, right? The part where both cars brought in at time zero is a bit irrelevant, right? Why? Does it work on one car, right? It doesn't matter which one, right? MJ only starts after the other one is finished, right? What does that mean? That means that the time, right, for one of them to finish is plus, right? You have to take a look at the sum. So the probability that, right, x plus y is less than or equal to 2, right? Which will be into minus x plus y dx dy from 0 to 2 minus y, right? And y runs from where to where? 0 to 2, right? Not 0 to infinity, right? 0 to 2. Any question? All right, so I think that's really like the last part of the problem set. Okay, this one will be posted later on tonight or tomorrow, right? And you have, well, depends on what I think, or either until Friday or Monday to do it. All right, so let's take a look at the next one. Okay, so what's the next topic after joint distribution? The next logical topic, or the next topic to talk about, right, is transformation of joint distribution. And I think there was already like kind of a mention of this, right, from the lecture in the lecture last time. And the point, right, is that let's say you have x and y uniform, right, on the circle, right? Then x and y are not independent, okay? But intuitively, right, if we look at the polar coordinate of this distribution, in other words, right, if we look at the pair r and theta, where r is x squared plus y squared, right, square root, and theta is tangent inverse of y over x, then r and theta will be independent, right? But just out of curiosity, right? Let's just see if you understand this. Let's take this case where x and y are uniform on a unit circle, right? And if I define r theta like that, then what distribution does r and theta have? Marginally. Intuitively, right? I'm not saying that you would know it, but what distribution would r and theta have marginally? As a guess, basically. So here's a guess. That theta will be uniform from 0 to 2 pi. Which is kind of clear, right? The angle is uniform from 0 to 2 pi. However, right, r being uniform from 0 to 1 is not correct, I think. Y cell. Because when you think about it, right, when you select points uniformly on the unit circle, then the radius, because the uniform here is in terms of the area you choose, right? Then the radius, right? Probably you have to choose more points closer to the inside and less on the outside to make sure that the area is proportional. Pure guess, right? But I don't think, again, this is guess, right? I'm not saying that I know precisely, but R will not be uniform, right? Anyway, point being what? That all these guesses, hunches, blah, 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 right? And they are very natural transformation. And I guess if I fail to mention it, right, it's obvious that R and theta here are random variables, right? They have a joint distribution, joint PDF. So the technique, right, of transformation here will exactly tells you what the joint PDF of R and theta is coming from the joint PDF of X and Y. Okay. And actually it works for any kind of transformation. Basically, if you transform XY into a pair U and V, right, through a mapping like this, right, for example, like that, then basically, right, U is a function of X and Y, V is a function of X and Y, then this technique will tell you what the joint distribution of U and V is. And this is actually an old technique. Old, as in you should have seen this before, right? From calculus 3, this is the change of variables in multiple integral via the Jacobian, right? This is exactly what that is. Okay, so we'll use the Jacobian technique of the transformation of the multiple integral to derive the joint PDF of U and V from the joint PDF of X and Y. Right. Any question about this so far? Okay. So the one thing, right, that is very easy to get confused here is that we will look at the transformation on both sides, meaning we'll look at a vector X moving to vector Y like this, which is what you usually look at, right? X plus Y is U, X minus Y is V, right? But we will also look at the inverse movement from Y go back to X. Meaning, for example, right here, we will look at X is U plus V over 2 and Y as U minus V over 2, right? This is the inverse map from this, right? They're related and the Jacobians are related, but they're not the same thing. Use the wrong Jacobian and you get the wrong result. So it's very important to pay attention to which direction we're talking about. Okay. But, right, to help us distinguish, right, which direction, when we look at, right, the movement from X to Y, we denote the notation here as Jacobian dy or dx. This is my own invention as far as I can tell. I'm not sure if people do this, right? They might have other ways to do so, but right, for me, right, because the Jacobian literally represents that kind of multi-dimensional version of derivative. So we can say d, right, vector y over d vector x as a symbol for it. All right. And there you go, right? It's essential to distinguish the two directions, right? Any question? All right. Oh, and also, I guess here's one thing, right? One thing about the Jacobian matrix is which one is a row, which one is a column, right? You differentiate y with respect to x or yi with respect to xj. The point is actually it doesn't matter because we just take the determinant. And basically, right, the transpose, right, of the matrix gives the same determinant as the matrix itself. So if you switch the order, you just get the transpose of the Jacobian that I look at. But right, basically, we'll get the same determinant anyway. Okay. All right. So there you go. Right here for this transformation, right, the Jacobian for the forward movement from xy to uv will be this. The Jacobian for the other way around, which is from uv to xy, will be this. Right. And notice that the product, right, of these two matrices is an identity matrix, right? Which is not a coincidence, because if you map forward and backward, you just get the identity map. And a correlation of this, right? Oh, sorry, a corollary of this is that the determinant of this matrix is 1 over the determinant of this matrix. They're inverses of each other. Right. Any questions so far? All right. Well, this might be a boring transformation, right? As you say, because, well, it's too easy, right? Too simple. They're linear transformation, right? Let's look at something more exciting. And one thing that maybe is too simple here is because, right, this matrix is pure numbers, right? And that should not give you the wrong impression that the Jacobian matrix, right, are pure numbers. Again, if you remember from Calc 3, right, which I'm sure you all do, the Jacobian matrix, right, are functions, right? So this case, right, this example will kind of, right, show you what you already know anyway, right? That the Jacobian matrix are functions, right, of whatever variables that are the independent variables, right? For example, if we map from xy to uv, then the Jacobian are functions of x and y. If we map from uv to xy, which, right, notice is exactly the inverse map of this, then the Jacobian is function of u and v. Okay, so this alone will kind of is enough to warn us that we need to distinguish the two directions, because they're not the same, right? They are functions of different variables. All right. Any questions so far? Now, again, right, you see the same theme happen, right? Doesn't matter how complex the map is, actually, we still see that this is the inverse of that. Or as I claim, the product is an identity matrix. But here, right, I claim something strange is happening, or it might look like I'm a little bit crazy, right, in terms of my claim. Why would my claim look suspicious? Why would my claim look suspicious or strange? Or why should you question the result? You should question the result, right? Because, well, this is a matrix in x and y. It's a matrix in u and v, right? When you multiply them, you get a mix of x, y, u, v. How could they simplify to 1, 0, 0, 1? How's that possible? If, right, they're both in x, y's, or they're both in u, v's, right? Okay, right, maybe the calculation looks a bit tedious, but you can trust me on that. But here, right, x, y, and u, v are just don't mix, right? Like oil and water. How could I multiply these two and I get 1, 0, 0, 1? Am I crazy here? You should stop listening to me if you haven't done so already. Well, the answer is they are not just isolated symbols, right? X, Y, U, V are related. For example, right? Of course, this has to be expressed as in terms of U and V. But if you look at square root of V over U, right, what is it? That right there is 1 over Y. This is Y, for example, right? And this is 1 over X. And this is, I guess you can solve it out, right, in terms of X and Y. Well, the point is, right, all these terms can be traced back into X and Y. And so therefore, when you multiply them out, right, they are not just 4 different symbols. They have connections via either this or that. And so when you multiply them out and take into account the relationship in terms of the, what's given right here, you will get the identity matrix. Okay. Any question about this? All right. Yep. So here, right, this is the general properties that we just kind of saw from those 2 examples. That if you map forward and you map backward, then the 2 Jacobians are inverses of each other. And that can be derived by a chain rule, but this is like a multivariate chain rule, right? And the determinant, right, will be 1 over the determinant of the other by the, kind of inverse property, right? Any question about this? So this is just basically the general result that we've been talking about. Okay. So, well, what's the point of discussing all this? The point is, here is a fruit of our labor, right? Starting out with a joint PDF that's given. So you should look at X as the PDF that's given here. And this is the to be found, the 1, right? Then it's actually a formula you can use, right? It can be proven, or the proof actually is from the change of variable formula in the Jacobian, right? The one that you learned in Calculus 3. But the PDF of Y will be, right? You have to read this very carefully. It's a PDF of X, plug in the expression of Y, the expression of Y when you solve for X, in terms of X. And then time multiply with the absolute value, right? Okay, this is the absolute value of the determinant in the right direction. And the right direction here, notice, is the X over the Y, so it's the inverse direction. So you map X to Y, but the Jacobian you use here is the inverse of the Jacobian. And I guess it helps to remember that this is also the inverse. Map that you plug into the joint density of X. Okay. All right. So that's crazy, right? How do you memorize all this? Well, it's kind of self-guide if you do not lose track of what symbols you must use. So because, for example, right, basically the end result means that everything must be in terms of the target. So in the language above here, everything must be in terms of, let's say, U and V, because that's the target, right? And notice only the Jacobian of the inverse have the variables as a function of U and V. Right? If you use the wrong Jacobian, you get a function in terms of X and Y. So if you get the wrong variable, you know you're working on the wrong direction to begin with, right? And same thing for here. You have to plug in expressions in terms of U and V. So you know you have to use the inverse function anyway, right? Any question about this result? All right. So these are the remarks I think that I just talked about right before. So these are just the kind of like again right re-emphasizing all these points you need to pay attention to. Oh, yep. This last one I didn't tell you, so this is actually very important. The formula itself, right? This one just gives you the form of the joint density, right? In terms of the problems we just did, is something like this. Yeah, it only tells you this much. That's what the formula tells you. These parts are not in the formula. You have to figure that out. And you understand how important to figure that out too. Because if you just give the answer like this alone, is not enough, right? Because you see, this region plays a big role, right, in that being a density. Okay, so the difficulty, of course, right, is that by the time you get to this part, you're like, okay, I've done a lot of work. I should stop because I'm done. The answer is no, not yet. You still have to find out the support of y, right? If you don't do that, your work is not complete. Right? Any question? All right, so let's take a look at some examples, right, to see how our work pay off. All right, so here we start out with, right, the independent on the unit square. And we do this map, right? X plus y, x minus y. First of all, right, any guess on what UV should look like if you do this? What is this transformation? I think, right, basically it will do something like a rotation like this. But, right, intuitively. So it seems like UV should still be uniform, but on a very different region. All right. Well, that's a hunch. Basically, when you the more intuition you try to make out these things, the more you understand the problem. Right. That doesn't mean that you should commit to your guesses and like I must be right, right? But let's see. So, right, this is the joint density you start out with. Then you have to solve for x and y in terms of u and v because you have to find the inverse function. Then you have to find the Jacobian of that map and find its determinant, right? Then you plug in, right? You see, you plug in this is a constant, so there's nothing there, right? Multiply with the absolute value of the determinant. So, like I said, right, that just seems that this is that, but incomplete, right? We know why it's incomplete. Because the support, right, of U and V are not given. And you see, right, with this kind of shape, the support of UV will be super important here, right? So what is the support? Well, you have to find out on your own from the forward map, right? So basically, because of this, U and V are the region bounded by these four lines. So yeah, right, looks like that. You know, rotated triangle, square that I draw before. Right. So without this support, right, without saying the support here, then your answer above will be incorrect, will be not complete. Right. Any question about this? All right, very good. So let's continue with this on Friday. Okay.
Have a good one.
You too.